Alrighty, hello everyone. Welcome to our very first class. Let me go ahead and share my screen really quick. Okay, awesome. So I've got our icebreaker up on the board. If you guys want to go ahead and answer that, that would be awesome. And then we'll go ahead and get started at 7:05. If I can. Okay, there we go. Disable annotations. Amazing. All right, so our question for today is what cartoon character would you want to be? I don't know, like how many of you guys watch like cartoons these days? Because you guys probably don't have cable anymore. So cartoons are like not a thing. I don't know. We'll see. But I don't know how many of you guys like watch real cartoons. All right, let's see what everyone says. Okay. Um Cool. Okay, Jason says he does not want to be any cartoon character. He just wants to be himself. That's amazing. Good for you, Jason. And Vika says, what do you mean? Oh, did I say first meeting? For some reason, I don't know why I said first meeting. Welcome to like our fifth class, or something. We have been here for definitely more than one meeting. Okay, Cypher says Mr. Impossible. Okay, that's a good one. Yeah. Mr. Impossible. Sweet. Okay. Ari says gumball. I think you mean gumball, right? Not gumball. I'm gonna assume you mean gumball. That's like the yeah, I think I remember that one. That's a good show. Uh that's what I watch in hotels. Minnie says Jerry from Tom and Jerry. Oh, I love that. Yeah, Jerry's so awesome. Sometimes when I'm just like bored and I don't want to watch anything else on TV, I'll just like put on some Tom and Jerry. It's great. Aditya says none of them. He just also doesn't want to be a cartoon character. That's okay. Amari says Loki not a cartoon, but I would be a Power Ranger. Okay, yeah, Power Ranger I would yeah, I know it's not a cartoon in the animated sense, but like I would put Power Ranger. I would consider that a good answer. Okay, cool. Nez says oh Naz, sorry. I don't have my glasses today. I'm getting a new prescription, so I'm just like really struggling to see everyone. Okay, Naz says any cartoon character with superpowers. I feel like that's like most car well, actually no, that's not true. There's yeah, never mind, that's not true. I mean, I guess if you're looking at like an animal cartoon, like their superpower is being able to talk as an animal. So I guess like that counts, but aside from that, I don't know how much there is. Yeah, Nahal says including anime. Yes, we can include anime, though I won't be very familiar with a lot of anime characters. Um, cool. Cyberneat says gumball is so tasty. I don't know how to feel about that. That is a very odd sentence. Let's see. Oh, Ness says my name is Zia. Okay, cool, cool. You guys should have the ability to rename yourselves. I think if you click the three dots in the corner, or maybe I can rename you. I don't know. We'll see. Alrighty. Kavya says Bluey. Oh, I love Bluey. Actually, there was like a study recently that showed like Bluey helps little kids make better decisions. So watching Bluey is good. All right, let's see. Oh, Jaden said, or not Jaden, Jason says One Piece. I've definitely heard about this, but I've never watched it. I think I don't know. I think it's a TV show. I don't know. Maybe I'm like thinking of something else, or like a manga. I'm not sure. Okay, yeah, Ari says Gumball. That one's good. Yeah. Anvika says Ash Ketchum from Pokemon. Sweet. I was never a Pokemon kid growing up, so all I know is Pikachu, as generic as that is. Let's see. Who else? Ooh, I bet he says Cuphead. Oh, I don't know who this is. This is new to me. Maybe I'll Google them later. Wow. Yeah, Cyprian says, okay, One Piece is a long show. That's what I thought. I think it's a show, right? Okay. That is what I thought. Rohan says Captain Underpants. Oh man. You guys still read Captain Underpants. Like that is so cool. Wait, actually we had this like I feel like we had this discussion before that you guys still read like Captain Underpants and Dork Diaries, which is like crazy because those are books that were coming out when I was a kid. I don't know if those authors are still releasing books. Okay, yeah, cool, cool, cool. We got a lot of answers. This is awesome. Okay, well, let's go ahead and transition to today's lesson since it is now 9:05. So if we can go ahead and maybe stop discussing cartoon characters, which is totally awesome. We could do a whole class on that. And let's turn to geometry. So today, we'll be going into a pretty, so last week we kind of started the discussion on like polygons and triangles and all that jazz, which is wonderful. Today, we're going to be really doing a deep dive into triangles, and one of the biggest topics in triangles is going to be similarity. Now, all polygons can be similar and congruent and whatnot, but we particularly care about triangles because triangles have a lot of special theorems like associated with them. So that's why we'll be focusing a lot on triangle similarity and congruence. Okay, so I'm throwing some of these words out. Can any of you guys define what like similarity is? Do you guys know what it means to be similar? Yeah, so let me write this out. Do you guys know what it means for triangles to be similar? If you know a definition, feel free to put it in the chat. Okay. Um, but he says that they're kind of alike, which is true. They are definitely alike. But like, in what sense are they alike? Because all triangles are alike in the sense that they're all triangles, right? So let's see if we can get a little more specific than alike. I like where we're going. Wow. But let's see if we can get a little more specific. Monique says where the ratio of all sides is equal. Yeah, so definitely like this idea of ratios. I like this. Can we maybe be a little bit more specific about like what sides for the ratios are equal? Like what sides specifically matter? Okay, let's see what else. Yeah, Zia says they're like kind of the same. That's true. Um, Aditya says they have something in common. Right, right. And Vika says proportionate measurements. Okay, I really like this one. I'm gonna write this one down. Um, Proportionate measurements. And we'll come back and talk about this. I just want to see if there are any other answers. All right, what else do we have? Amari says to have similar qualities, vertices and sides. That is true, but remember, because all triangles have three vertices and three sides, that's not going to be a very distinguishing feature. However, if you're talking about side lengths, then I think we're kind of getting on the right track, like having side lengths that appear to be like similar or in the same ratio. So that's where the idea of ratios kind of comes from. Okay. Oh, Kavya says same shape but different size. And I really like this one. This is a very intuitive way of explaining similarity. I'm going to abbreviate different as DIFF. Okay, cool. Um, Nahal says the same sides and angles. Nahal, you are like 50% of the way there. Similar triangles have the same angles, but they do not necessarily have the same sides. And we'll talk about like what does have the same sides, but you're very close. Okay. Yeah, so they'll have proportionate measurements and congruent angles. I'll write that as well. Congruent angles. Okay, amazing. All right, so I see a lot of different answers, and this is good. I think this is a good place to start. So, for triangles to be similar, a couple of things have to be true. First, if I have two triangles, then their angles have to be the exact same. If all the angles in two triangles are the same between the triangles, then we know those triangles are similar. We don't have to see anything about the sides. As long as we know that the corresponding angles are the same, then we can say that these two triangles are similar. Also, in addition to like congruent angles, you also have measurements of sides that are going to be proportional or in the same ratio. Now, the ratios can be constructed in different ways. For example, you could say like, oh, here's the ratio of three sides in this triangle. In this other triangle, the ratio of the three sides also happens to be the same. So that means that those two triangles are going to be similar. Or another way you can do this is kind of by comparing the ratios between each pair of corresponding sides. And if all of those ratios are the exact same, then you know your triangle is similar. So this might seem like very theoretical without a diagram, and don't worry, we'll get to a diagram. But to help you guys understand this a little bit more intuitively, think about like when you're putting an image in like Google Docs or Google Slides, like you're making a presentation or something, and you take your image, it's like really blown up, right? And you want it a little smaller. So you're gonna click the thing at the bottom and kind of just like move it along a diagonal, right? You're just gonna ch change this shape. And actually, maybe we can demonstrate this here, because I actually do have shape drawing tools. Yes, yes, I do. Amazing. So here's like one triangle, right? So I have this triangle, and all I'm gonna do, first I'm gonna make a copy, if I Okay, yeah, here is my copy. And you know what? Let me actually, hold on. I feel like this is a bad triangle because it's very like, how do I make it like not, okay, whatever. It's fine. Here is another triangle. So what I'm gonna do is I'm gonna take one corner and I'm just gonna drag it. And I'm gonna drag it inwards. So all I did was move it along the diagonal. And if we go ahead and like pull out our protractor and pull out our ruler, we'll see that all three of the interior angles are going to be the same. So I'm going to draw that like this. So this angle is going to be equal to this angle. This angle over here is going to be equal to this angle, and this angle over here is going to be equal to this angle. Remember like the notation with the tick marks? If two angles have like one tick mark, that means they're equal. If they have two tick marks, then they're also equal. So anything that has like same number of tick marks are going to be equal. But these three angles would not be equal because they each have different tick marks. This is like kind of our way of using variables with angles, but because it's really hard to put like letters in here, like this is why we use tick marks instead. Okay, awesome. So Cypherny says size does not matter. That is correct. Size doesn't matter because all we're doing is just changing like the kind of like the proportions between it. Like the proportion stays the same, but we're just changing like how big it is. So this is kind of like dilation, if you guys have heard of that. If you guys have done translations before, we're just dilating the triangles. Okay, so you're just dilating. So all you're doing is kind of just dragging a corner and moving it up and down. Okay. I see someone says, can we use one tick mark for each? No, because we don't know if these three angles are the same. So that's why we have to use different tick marks. You use a different tick mark for every different angle. But because we know that this angle and this angle are the same, we can use the same tick mark. Okay, hopefully that makes sense. Cool. Amika says, isn't dilation the same thing? Yes, dilation is like how we get to similarity. Yeah, they are absolutely the exact same thing. Okay, wonderful. Also note that you can make this triangle bigger and it would still be similar. So like whether you make it bigger or smaller doesn't matter. Okay, so that's what it means to be similar. One thing to note is that the proportions between the sides are going to be the same, meaning that this side over here, if I call it A, and this is X, and this is B, and C, and then like Y and Z, then A to X is going to be equal to B to Y is going to be equal to C to Z. So all these three ratios are going to be the same. And the reason why that is because we are taking corresponding sides and we're just measuring the ratio. And the definition of a similar triangle is that corresponding sides are all similar. Notice that you can't just have two sides with the same ratio, like all three have to have the same ratio. Okay, cool. So this is like a definition of similar triangles. Let's go ahead and like kind of take a look at this in practice. And let's see what you guys think. So I'm gonna give you guys like a diagram and you guys let me know like if you think these triangles are similar. But first, I need to make the diagram like actually visible. Okay. All right, so take a look at this diagram and let me know. Do you guys think that DCE is similar? Or actually, maybe I shouldn't even tell you. Do you guys think there are any similar triangles in here? And if you do see similar triangles, can you provide the relationship? Can you provide which triangles are similar? All right, let's see. I think I like gave it halfway, but it looks like some people are still getting it. Okay, I do see one question. What is the relationship between what we are learning now to the subject we are learning today? Oh, today is what we are learning now, because we are now learning about similar triangles. So this is like a pretty big topic in geometry. A lot of problems that seem complex can be simplified using similar triangles. Okay, cool. All right, I see a lot of people saying yes. I do see some similar triangles. And the ones that I'm seeing, so people are saying that DCE is similar to ACB. Okay, awesome. And I think most people are agreeing with this. Okay, yeah, okay. So it seems like we're in a lot of agreement here, which is awesome. Alrighty. So, something cool to note is that if a segment is like parallel to one side of the triangle and it intersects the other two sides, then the resulting triangle is going to be similar to the original. And the like intersected sides are going to be like proportional. So this is like a really cool thing. And this kind of like diagram will come up a lot in like bigger geometry problems that have like 50 different moving parts. Sometimes you'll see this like cute little triangle intersection thing, and this can actually provide a lot of insight. So let's break this down. Let's show that these are actually similar, okay? So what I'm going to do is I'm going to go ahead and extend this line, like so. Okay. Um, so let's say this is angle, technically this is going to be angle, we'll just say it's angle A, that's fine. And we'll say this is angle B, okay? Can you guys tell me what, or hold on, let's do a little more line extension. So this is like super duper easy to understand. Okay, and then I'll do like this blue over here. And I think that's an orange, but I accidentally used yellow. That's fine. Okay, can you guys tell me what this angle will be? This one over here. Okay, I see a couple of answers. Oh, we cannot say there's a measurement. We cannot give any like numerical answer because we don't know what the actual value of these angles are, right? So in terms of A, can you tell me what this angle is going to be? This AD something. Yeah, it is going to be an acute angle, and I do see a lot of people saying that it is actually going to be equal to angle A. So great job, Atul, Anvika, 6-7, maybe you can put your name, Vishith, and yeah, okay, really good work. And then yeah, Kavya Arade. Wow, so many people. All right, so this kind of goes back to what we talked about like earlier in the geometry session with vertical angles, right? Remember how we said vertical angles are equal? So that means if this angle is A, this angle is vertical to it, so this is also going to be A. But we know that these two angles are corresponding to these two angles. So if these two are A, then these two are also A. So we know that angle CDE is A. What do we think? Okay, awesome. Cool, cool, cool. All right, so can you guys tell me what angle CED is? Yeah, it's just going to be angle B. So great job, Anvita and Kavya and Cyperneath and Aditya and Nihal, I think is 6-7. But yeah, okay, really great work. And oh my gosh, so many people that I would love to give shout outs for, but I just can't because you guys are all so fast. This is an awesome sauce. Okay, so we know that we see some common angles. And obviously, like angle C is, we'll just say it's angle C, right? So let's go ahead and take a look at these angles, right? I see that I have like, if I have triangle DCE, that's going to be one triangle, right? Now, if I'm looking for a similar triangle, I want all my angles to be similar. Now, we can't say anything about the sides right now because we have literally no information about side lengths, but we can look at the angles. So if I look at angle A, I can see that angle A and angle D are similar. So I'll write down A as part of one part of my triangle. Then if I look at angle C, I'll see that obviously angle C is equal to itself, right? In both triangles, this angle is the same, like nothing fancy is happening to it. So we'll say angle C goes next. And then finally, angle E over here is going to be equal to angle B over here. So we're going to go ahead and put B at the very end. So if you guys look at how these angles are kind of lined up in the triangle, we'll see that D is equal to A, C is obviously equal to C, and E is obviously equal to B. So we know that DCE is similar to ACB. Okay, so kind of breaking this down. A couple of really important things to know is whenever you're like listing a pair of similar triangles, it is so important, and I cannot emphasize this enough. It is so important that you put the vertices in the order that they're corresponding to. Okay, so in this case, angle D is equal to angle A. If I had instead written this as angle DCE, or triangle DCE is similar to CAB, like this would not be a valid similarity, right? Because D and C are not equal, C and A are not equal. So this is not going to be like a pair of similar triangles. Instead, I have to make sure that my similar triangles are in the right order because that's going to help with like setting up ratios going forward. So this is like super duper important to remember. Okay, I do see a quick question. Hall asks, is this an equilateral triangle? No, this is not an equilateral triangle. We cannot say anything about what this triangle is. Okay, cool. All right, so that's like one big thing. Also, I realized I started using this symbol without saying what it was. This is just how we say similar. So this is mathematical notation for similar. Okay, awesome. So how do we feel about this? Is this like okay, understanding how this works? Cool. So the big idea here is all we did in we had like triangle ACB. And then all we did was we added like a kind of line that's parallel to one side and cuts the other two sides. And once we add such a line, then we create some similar triangles. Notice that I could also have the same thing kind of going like this. I could also have a line like this. And this line is going to be parallel to CB, and then I get to other similar triangles. So this is like pretty important. You can kind of think of this as like a transversal because it is like cutting across two different things. We don't really call it that, but you can think of it like that. Okay, awesome. Cypre says what happens to the equal sign. So there is no equal sign in transversals. It is just this thing. This is going to be our similarity. Okay, cool. Yeah, I know. It's like it is sad. You don't really use equal signs in geometry, like now that I think about it, unless you have like some variable stuff going on. Okay, cool. So in general, if you have like three parallel lines, oh, actually, just kidding. This is for something else. We'll talk about that. Okay, so I'm gonna go ahead, clear out this diagram, and let's talk about another kind of example. Okay, so this one I think will, I don't, yeah, I guess this one's not like super specific to triangles itself, but see if you guys can find like, do you guys see like any proportionate segments here? Are there anything that's like gonna be in the same ratio, similar? Yeah, okay. I see Cypress says, oh wait, no, never mind. I think that was not in response to this question. Okay, and Vika says A is to B and C is to D. Cool. And Cypress says A and B. Cool, cool, cool. Okay, so it seems like Shonik, Nahal, and Imni all and Vaivehi. Okay, awesome. All agree on like how this works. Right. So this is really cool. Basically, we'll see here that A over B is equal to C over D. Okay, take a minute and see if you can like understand why this is true. If you can't, like if you're like, okay, where's this relation coming from? Let me know in the chat. We will talk about this, but if you're just like lost, like what is happening, like put it in the chat so that way we can break this down really clearly. If you know what's going on, put a smiley face or like put a thumbs up or just say like, yes, I understand what's happening. You are not lost, Nihal says. Awesome. Okay, Athol says yes, he's doing lovely. Tharp says yes. Okay, awesome, awesome. Great. I think we're good. Yeah, Minnie says because the numerator and oh yeah. Minnie, let's kind of break down this reasoning, right? I think you get it like intuitively, but we kind of need to like I think we need to be a little more rigorous. I think you get it like very intuitively. Let's see if we can like formally show this is true. Okay. Um, so a couple people get it, couple people don't. Let's break it down. Okay, basically, we're not really going to be talking like this is not very much triangle related. Instead, this is going to be looking more at proportions. So in general, if you have three parallel lines, notice that these three lines are going to be parallel, and they intersect two transversals. These two are going to be our transversals. Then the transversals are going to be like divided proportionally. So these two are going to be in the same proportion. Um, Okay, and so basically, we can kind of like, I guess, okay, see how if you like extend these two up here, you'll get like a little triangle like hat thing at the top. If you go ahead and do that, you'll see like once again, there's gonna be like three pairs of similar triangles. And actually, let's see if we can draw this to make it like clear, because I think this is pretty interesting. Sometimes sometimes if you don't have triangles, draw triangles, and that can make problems easier. Okay, let's see. So I'm gonna draw like this. I hope I like kept that parallel. Oh no, I definitely didn't. Yeah, they don't actually have to be triangles to be similar, but I find this helps a lot of students like visualize it. Okay, so I see lots of similar triangles. Yeah. I see this triangle. Whoa, it was like very poorly drawn. This is one triangle. I also see this triangle. And then I see a third triangle. Wow, these lines like totally stuck, you guys, but I hope you guys can see like which triangles I'm talking about are similar. Okay, and then this triangle in purple, which is like the big one. Okay, so those are my three triangles. Looking back, this is like very bad drawing, but it's okay. All right, so we kind of talked about how like in the previous problem we had a triangle and we had like a line that was going to be parallel to one side and cuts across the other two, right? So if we look at like the green triangle and the blue triangle, that is exactly what's happening. So we can kind of say that like A and C are going to be proportional to each other. And then similarly, B and D are going to be proportional to each other. And that's why we can write a relationship that's kind of like this. Okay. Um, cool. Does this make sense? Is this okay for everyone? Okay. I think we are good to go. Awesome. Dora says, so basically they don't have to be triangles. Yeah, that's correct. So you can actually have like these proportions and stuff even without triangles. It's just most often like you'll be working with similarity in triangles. And I find that like drawing triangles can actually help find similarity sometimes. So that's something to consider for sure. Okay, cool. All right, we are doing awesome, you guys. How many of you guys are like familiar with this kind of stuff, like similar triangles, congruence, and things? Okay, pretty familiar. This is good. Okay. Yeah, this is like I definitely remember learning this in like eighth grade. So this is definitely eighth grade stuff. But if you do like a lot of competition math and things, these definitely pop up. Okay, so I want to talk about just like one really quick similarity theorem. And in the future, we'll dive into like some of the other bigger ones. I just want to talk about this one because it's very easy. We've already like kind of mentioned it. Okay, so how many of you guys are familiar with angle-angle similarity? How many of you guys are familiar with this? Okay, so Atul and Vika, Kavya, Vaivehi, Adar. Okay, so we got a little bit. Shauna says, not me. Rohan says, I think. Okay, cool. Cyprany says he knows it. Okay, awesome. So I think we're like pretty split here. So let's go ahead and take a look. Yeah, okay. Alrighty, so basically, what angle says, and let's go ahead, and maybe it might help if instead of like writing it, I kind of just give you guys like a good definition and you can see like where this comes from. Um, don't worry about like copying this down or whatnot, because all of this will be provided in the handout afterwards. So just go ahead, like take this in, understand what it says. Um, and yeah. All right, so the angle-angle theorem says if you have two angles in one triangle that are equal to two angles in another triangle, then the two triangles by themselves are similar. Okay, so let's break this down. Remember when we first started talking about similar triangles, we said that all their angles have to be congruent. I think you guys like got this idea pretty well. Now, what this theorem is saying is that if I have two angles in one triangle that are the same and two angles in another triangle that are the same, then those two triangles are actually going to be similar. And you might be like, okay, Sam, we know that all three angles have to be the same. So how can we just say two triangles are similar based on only two of the angles? Well, remember what we learned about the sum of the degrees in a triangle, right? We said that the sum of the degrees in every triangle is 180. So if we know two of the angles, we can very easily calculate the third angle. And if the two angles are the same in both triangles, then that third angle is going to be the same in both triangles as well, because all three angles have to add up to 180. So this is where this theorem comes from. I think this is like the easiest similarity triangle theorem to remember. Because it follows like pretty easily from one of the main theorems. And this is the easiest one to show as well. Like I think this is one of the ones that gets used the most. So this is like one of the big conditions for similarity. All right. What do you guys think? Okay, let's see. Let me look at the questions. Yeah, Maneet and Cyphernes says 180 degrees. Yeah, that's absolutely right. Good comments, Maneet and Cyphernes. Vaivehi asks, what does AA stand for? It stands for angle. Yeah, let me write that out. Angle. Good question. So in a lot of similarity theorems, you'll see like they're abbreviated like AA, SAS, like AAS, like all of these kinds of things. A will stand for angle, and S will stand for side. And we'll talk about some of these in a future lesson, but I just wanted to bring up this first one because like this is very, very easy to learn. The other ones take a little to grasp. Okay, so I think we're all doing pretty well. This is really great, you guys. Okay. Uh, is it the same for any shape? Yeah, okay. So Cypernith asked, does angle apply to all shapes? The specific one where it's like if two angles are the same, that only applies for triangles. Now, if you're looking at other polygons, like let's say you're looking at pentagons and you want to show like two pentagons are similar, then you need to have like at least four angles have to be the exact same. And if four angles are the exact same, then you can say those pentagons are similar. But if we're looking Okay, normally you don't deal with problems with similar pentagons. Normally you deal like mostly with similar triangles. So that's why we kind of focus a lot of our similarity stuff on triangles. But yeah, that's the big thing. Okay, yes, cool. Okay, so Nahal asked like what does angle really mean, right? Like that doesn't seem to be making sense, which is okay. So what angle means is that we're trying to show like two angles in each triangle are the exact same. So that's where this name comes from, right? So if we have like two triangles like so. And let's go ahead and, oopsies, make a quick copy and decrease this. Okay, so what we're saying is this angle, which we'll call A, and this angle, which we'll call B, this angle we'll call A, and this angle we'll call B. These two are angles that are similar. So these two are angles that are similar. And these B angles are angles that are also the exact same. So because we can achieve similarity based on just knowing these two angles, we'll say that this is angle theorem. Okay, it's just like a name. So yeah, don't stress yourself out about that. Okay, awesome. So let's see. What do I want to do now? All right, let's go ahead and do some problems. I think this is a good time to transition into problems because you guys seem to be getting the hang of this pretty quickly. Um, cool. Let's do one quick thing. Just we'll do like a pretty easy example just to like concept check. And then we'll go into some more difficult problems. Yeah, I see a lot of you guys are like, yes, this is super easy. Let me tell you, similar triangles can get like kind of brutal, like going forward. There can be some like pretty tricky problems where the similar triangles are like impossible to see. And like if you spot them though, the problem gets dissolved to like 30 seconds or 30 seconds of work. Um, but sometimes similar triangles are really hard to see. They're super important though. I would say they're like one of the biggest problem solving techniques in a lot of math competitions and a lot of like math problems in general. So it is important to understand how similar triangles work. Obviously, the problem I have displayed on the screen is pretty easy, and most of you guys have gotten an answer. We can show that these two angles obviously match each other, so these two triangles are most definitely similar. Can you guys say what like angle C and angle F are going to be? Yeah, they're also going to be 70 degrees. So this is very much like not an accurate diagram, but that's okay. Sometimes diagrams aren't accurate. So yeah, we can say angle C and angle F are going to be 70 degrees. And this just further confirms that these two triangles are 100% similar. Okay, awesome. Yeah. Okay, so how is it 70? Right. So in this case, remember that the sum of the degrees in the triangle is going to be 180, right? And we know that one angle is 40 and the other one is 70. So that last angle is going to be 70 degrees. So that's where that comes from. But yeah. Okay. Awesome. All right, so basically, if you have similar triangles, the reason why they're important, which we kind of talked about before, is going to be most often their sides. Their sides are going to be proportional, and that means you can use ratios of missing sides, or you can use ratios of like existing sides to find out missing lengths. So that's like a pretty big thing. Okay, cool. So let's go ahead and do some more challenging problems. I'm glad we did this concept check because I just wanted to make sure we're all on the same page. Now we'll get a little bit more into the thick of it. Okay. Well, okay, I guess this is not really the thick of it. I guess this is also like a good concept check. I lied. I didn't think about this problem. Okay, this is like pretty simple too. Are these triangles similar? The diagram is not to scale. Yes. Okay, wonderful. We don't have to spend too much time on this. Like this is pretty easy, you guys. Because P is equal to X and Q is equal to Y, and for sure R is equal to Z. These are supposed to be equilateral triangles. I don't think this XYZ one is very equilateral though. Okay, cool. So I'll just get rid of this. This is pretty simple. Let's go ahead and do an actual good question. Let's do a really good question. Okay. Wait, I lied. I got the wrong part. Okay, so quick note, the labels on this diagram are a little wonky. So I can rewrite them if it's difficult to see. I feel like I haven't used orange yet, right? This is gonna be 2, this is gonna be X, this is gonna be 4, this is gonna be 8. Okay, go ahead, take a second to solve this problem. Okay, I see quite a few people saying that X is going to be equal to 4. Alrighty. Let's see if that's right. Okay, so we are told that these triangles are similar, so let's go ahead and set up some ratios, right? Now, can you guys tell me like, okay, we know that ABC is similar to DEF. Can you guys tell me like one ratio of sides that we can set up? Like what is one possible ratio that we can say is true? Yeah, so we can say that AC divided by DF, right? We can make this as a ratio. Oh wait, not DF. It should be. No, it is DF. Sorry, I looked at those letters wrong. Okay, yeah. So AC to DF, like that's a good ratio we can set up, right? And if you guys are like, oh, where did this come from? The reason why, and this kind of goes back to like why I really, really emphasize that it is so important to ensure that these two like vertices are in the same order. Because when the vertices are in the same order, you can very easily like pull out each vertex, like the vertices to get similar sides. So in this case, what we did was we took A and C, right? So hold on, maybe underlining is gonna work better. So then what we're gonna do is in the second triangle, we're gonna take the vertices that are like corresponding to A and C. So D corresponds to A and F corresponds to C. So when we form our ratio, we'll make sides AC similar to DF, or proportional to DF. So that's where that first ratio comes from. We can also say that AB divided by DE is a potential ratio, as well as BC divided by EF. How do you guys feel about this like chain of reasoning? Okay, this is all good. You guys are like zooming through this. Okay, so let's do a quick question. So then if we go ahead and solve for this, we want to find BC, right? So we'll say AC, we can honestly we have so much information, we could do any of these. I'll do like AB over DE and BC over EF. So AB is 3, DE is 6, and that's going to be equal to BC, which we said is X, and EF, which is 8. So then X is equal to 4. Pretty simple. Okay. Cool. Let me go through the chat and see how everyone is doing. Um, okay, cool. Yes. Okay, so a couple of you guys are asking for a really hard one. Yeah, the next problem we're gonna do is gonna be more of like an applications-based thing. Um, and then maybe next week, like next week, instead of doing a lot of like lecturing and stuff, maybe we'll just do like a bunch of super hard problems because that can be equally fun. Yeah, today we're kind of just like gonna introduce similarity. And if I have more difficult questions, I will definitely try to pull them up. Okay. Um, cool. Now I'll ask how I can write fast. Yeah, I have a pen and tablet, so that certainly helps. Okay, lovely. We are all on the same page. Okay, before we go on to this next question, I just want to clarify one thing. So today we talked about similarity. Something that's like kind of similar to similarity, wow, that was weird, is congruency. Except what's different about congruency is that the triangles are the exact same. So they are copy paste of one another. There is no like dilating, size changing, none of that. Like the side lengths are the exact same. And we'll represent congruency like this. So it'll be the similarity sign, but it'll also be like an equal sign underneath it. So this is how we say congruent. Okay. Um, and so there's not a lot with congruent triangles. It can just make it easier to find like, oh yeah, these sides are the exact same. But showing the two triangles are congruent is a little harder, in my opinion. Um, but yeah, okay, cool. That was just a small thing. I just want to make sure we're all on the same page there. Alrighty, let's go ahead and do a challenging, hopefully. Okay, actually, I don't know. Maybe because you guys are like saying that everything is super easy, so maybe this might not be challenging. We will see. We will see. Okay, I will make a note to myself for next week to give you guys like challenge problems since most of this is like pretty easy for you guys. Or maybe like the homework will be challenging. I don't know. We'll see. I'm sure some of you guys have seen something of this sort before. But yeah, take a look at this question and see if you can answer it. And in the meantime, I will look for more difficult ones. Oh, okay, never mind. I have a good one that's pretty difficult. Okay, Rohan says he's done this one before. Yeah. I think this like pops up on the SAT every now and then. I feel like this is like on the SAT when I took it. But Becky, I do not think we were on week 2. I believe we were on week 4 or week 5. Yeah. Okay. Cool. I don't see answers immediately, which tells me that this problem is a little more challenging, which makes me feel better now, that you guys are being challenged because I don't want the entire lesson to be like easy peasy. Okay, I do see an answer from Manit and Nahal, and I don't know if I agree. And Rohan. Okay, I do see an answer from Kavi, which is a little different. All right, so it seems like our answers right now are 300, 360. Let's see if anyone is giving anything similar. Oh, Cypernite says it can't be over 180. Okay, very interesting. Interesting. He says also 300. Manit says it is height. Yes, that is right. Cypernite, make sure you're looking at height. I think that might be one thing to be careful of. Yeah, there you go. Okay, let's see if we have any other answers. It seems like a lot of you guys are, I feel like for the most part, people are saying 300. And I saw like one 360, but let's see. Any like agreements, disagreements? Okay, Anvika also says 300. Cool. All right, let's take a look at this question. So let the flagpole be AB, right? So we're gonna I guess like the diagram kind of helped for sure. You will not be given this diagram very often. Okay, so we'll say like this flagpole is going to be segment AB, and this little boy over here is going to be ED. So we've got this light source up here, and this is like point B, right? The light source is at point B. So the shadow of the boy is going to be like from D to C. So this is the boy's shadow. The flagpole shadow or the lamp post shadow is going to be A to C. Okay. Is everyone okay with these definitions? Like, does this diagram make sense? And like how we're getting these triangles. Okay, cool. I see lots of head nods, which is awesome. Good. So this helps. Sometimes people will like approach this problem. So the actual problem itself is just these like 3 sentences down here. But the actual problem like will not come with this diagram. So drawing this is like I would say 60% of the battle. So make sure you draw a diagram and understand like, okay, these are my relationships. These are the sides I'm trying to look for. All right, so first, we want to show like that there's some kind of similarity relationship. And I feel like this is pretty simple because one of the first things we talked about today is that if we have a triangle and we have a line inside the triangle that is parallel to a side of the triangle and intersects the other two sides, then we have a similar triangle. So let's go ahead and take a look, right? I have triangle ABC. What angle corresponds to angle A? What angle could correspond to angle A? What do you guys think? Yeah, angle D. Good work. Okay, what about angle B? What angle could correspond to angle B? E. Okay, awesome. And what about angle C? What corresponds to that? This one's like super easy. Yeah, C. Something I think Envika mentioned earlier was the transitive property. So that's why like C is equal to C. It's the same because they're the same. Nothing groundbreaking there. Okay, cool. So by angle similarity, like we can obviously say that these two are equal. So AA similarity is what we used here. Awesome. Okay, so since the triangles are similar, the ratios of their corresponding sides are equal. So let's go ahead and set up that like nice long chain of ratios, right? So we have AB over DE, and that's going to be equal to AC over DC, and that's going to be equal to BC over EC. Okay, what do you guys think of this? Is this like an okay set of ratios? Okay, see, I'm seeing like some head nods and some head shakes. So let's go ahead and break this down, right? Remember when we say that two triangles are similar, we say that their corresponding sides are going to be in the ratio together. So let's go ahead and look at each triangle, right? We can see here, like if we look at AB, for example, the side that corresponds to AB is going to be ED. These two are going to be in the same ratio. And the reason why we know that for sure, is because if we look at the vertices of these two triangles, notice how AB and DE are in the same position. This is how we can be sure that they are corresponding or related to each other. And even after doing lots and lots of these kinds of problems, I still use these vertices to help me determine like, okay, these two are going to be corresponding sides. So that's going to be like a good way to test like, okay, whether two sides are corresponding. All right, hopefully that makes sense. Let's go ahead and talk about where this comes from. Okay, cool. So let's go ahead and start plugging things in. We want to find AB, right? AB is what we don't know. Let's say this is our, you know what? We don't even need to bring a variable. We'll say it's AB. Okay, and we'll divide this by DE. Do we know what DE is? Yes, we do. We know it is 60 inches, so we'll put 60 over here. And you know what? I've been using too much green. Let's change this up. Let's do like a dark blue. So I have AB over 60. And this is going to be equal to, what else do I know? Um, I don't know. I mean, like I can find BC, but that's like too much work. Instead, I can do AC, right? We know that the boy is 240 degrees away from the flagpole. So if the flagpole is at A and the boy is at D, this distance is going to be 240. But we can't just put 240 up here, right? We need to find AC. So we also need to add DC, right? And we know that DC is the boy's shadow. So this is going to be 48. So this total thing is going to be 288 for AC. And then we divide that by DC. So we know DC is 48. So now we need to find AB. So before we do like cross multiplication and the whole jazz, let's go ahead and do some simplification, right? I know that 288 is going to be, well, actually, maybe I don't want to simplify like that. Maybe let's first start looking across. I can very much say that 60 and 48 have a common factor of 12. Well, I did not think when I used blue. Let's do red. It's like Star Wars here. Okay, so this is going to be 5 and 4. So that simplification occurs, and then 288 divided by 4 is going to be 72. So then if I go ahead and solve for AB, that'll be 72, whoops, times 5, which comes out to be 360, and that is the final answer. I think initially Kavya was the only person that said this, and I think she seemed like, I feel like looking at her camera, it seemed like she thought she was wrong. But you were 100% right, Kavya. A lot of you guys said 300. Let me see if I can like maybe guess where you guys went wrong. Um, let me double check my, okay, yeah, I think I know where you guys went wrong. So I think a lot of you guys just did AB over 60 is equal to 240 over 40. So you guys forgot to add the 48. But remember, always follow what these side lengths are saying, right? We don't care about AD. AD is not a part of any triangle. Instead, the whole side length is AC. So make sure you are always adding those parts. That's where like, this is like part of the reason why some of the triangles can get tricky. You have to be very, very careful about like what is the actual side length and what is only a portion of it. So this is like a pretty big thing. Okay, I know a lot of you guys said that it was easy, but also a lot of you guys ended up like making a couple of small mistakes. So are we good with this question really quick? Okay, Minnie asked, can we repeat? Yes. Just to quickly recap, so we showed that these triangles ABC and DEC are similar because they have the same angles. We used AA similarity. Once we showed that they were similar, we went ahead and set up a chain of ratios so that way we could find what the AB is. So we want to find AB, and we know a lot of other side lengths. So we have AB, we'll just leave that there. We know that DE, which is the boy's height, is 60 inches. So we'll say that AB over 60 is going to be equal to, we'll use the second ratio over here because we know both of those values. AC is going to be this bottom part. We are given AD and we are given DC separately. So to find AC, we need to add those together, and that'll give us 288. And then we divide that by DC. DC we know is the boy's shadow, which is 48 inches. So we do 288 divided by 48, and that's where this ratio comes from. Nahal asks where the 5 is from. The 5 is just from a little bit of simplification within the denominators. Yeah, so we canceled out a factor of 12 between both denominators, and that's where the 5 came from. Yeah, thank you, Saprani, for providing that as well. Good work. Okay, awesome. Yeah, so to conclude, the height of the flagpole is 360, not 300. Okay, let's do one more question. I just want to make sure this concept is good for everyone, because this is something that is very easy to silly. Adarav asks, how did I get AB? Yeah, so AB, I just let AB be AB. Like it was just like that was my variable, honestly. And then I set up the ratio with the other three side lengths, DE, AC, and DC, and then we solve from there. Does that make sense? Okay, awesome. If you want to break it down a little more, we can talk after class for sure. Okay, so let's go ahead. Okay, we have time for a couple more problems. I did want to give a harder question, but I just want to make sure we're all on the same page with how this works. So let's do another similar question. And if we have time, we'll do a hard question, but I don't want to rush you guys. Okay. All right, go ahead and take a look at this next question. Okay, I'm starting to see some answers trickle in, and it seems like quite a few people are saying 288, and I think we're in a consensus this time. I don't see a lot of disagreement here. Okay, let's go ahead and break this down, right? So first, let's go ahead and draw the diagram. Once again, my excellent drawing capabilities will be on display. Let's use a dark green. Okay, so we'll say the girl is 48 inches. This will be our girl. She will be this line. If you guys ever take physics, you will get very used to drawing objects as very weird shapes. Like you'll draw people as lines or circles, and like sometimes someone will say like, "Oh yes, imagine this cow is a sphere." That's a physics thing though. We don't really do that in math, except for this one instance, I guess. Okay. Anyways, we have this girl who is 48 inches. She is this line. She stands 180 inches away from a tree. So we will draw a tree. Oops, that line kind of fell off. Okay, and this tree stands. Oh, we don't know how long this tree is. We'll say it's this tall. This is a pretty big tree. Maybe it's a redwood. Okay, so this is a tree, and this is a girl. And we do know, however, the girl's shadow. So the girl's shadow is going to be 36 inches. So we'll say this is the girl's shadow. So let's go ahead and label some things. We'll say this is A, this is B, this is C, this is D, this is E over here. Now, let's see if I can draw a nice line connecting them. Okay. We'll do a little bit of adjusting. We'll do some adjusting because I drew this kind of bad. All right, diagram is not to scale, guys. This diagram is 100% not to scale. All right, let's label what we know. We know the girl is 48 inches, so we'll put a 48 over here. We also know that the shadow, which is represented by CE, is 36 inches. And we know that she stands 180 inches away from the tree. So the tree is A, she stands at C, this distance is 180. So, and also this is D. Okay, obviously, this diagram is like literally the exact same as the previous diagram, just a little bit of different context. So we can once again say that ABC is similar to DEC. If you guys don't understand where this comes from, make sure you review the angle-angle similarity theorem here. So once again, let's go ahead and set up our ratios. We want to find AB, and we know that AB over DE is equal to a, let's see, what can we use here? Oh, wait, I think I made an erroneous assumption. Oopsies. Okay. ABE is going to be similar to, aha, I messed up the vertices, you guys. CDE. Okay, there we go. That is now correct. So we'll say that AB over CD is equal to AE over CE. Is everyone good with this ratio? Do we all see where this comes from? I should put this in the museum. I don't know what museum would accept this work of art. Not very many, I assume. Okay, it seems like we're all good with this ratio though. So let's go ahead and start plugging things in. So we'll keep AB as is because we don't know anything here. We know CD is 48. That's labeled in our diagram. We know AE is going to be AC plus CE. And we know each of these lengths, so that's going to be 180 plus 36, or 216, divided by CE, which is 36. So let's go ahead and do some canceling. 48 and 36 are both divisible by 12. So if I go ahead and cancel a factor of 12, I will get 4 in the denominator here, 3 in the denominator here. 216 divided by 3 is going to be 72. So then I have AB is equal to 72 times 4. And I don't know why I ended up writing towards the corner of the screen. Let's scoot this over a tad. Um, oops. Okay, that's going to be equal to 288, like all of you guys have said. Okay, really wonderful work, you guys. I think you guys are starting to get the grasp of this. This is a pretty common like problem that's asked not just in like competitions or school math, but also in the SAT, if you guys think about that. But honestly, don't stress about that. That's like so long for you guys. Okay, cool. This is pretty good question. Pretty good question. Alrighty. It is 7:58, and we really don't have time to start that next hard question. Yeah, Rohan, unfortunately we don't. I will see if I can include it in the homework. And then for the next class, how many of you guys would like to just do like similar triangle problem solving? If you would like to, put something in the chat. Okay. If you would like for me to do some lectures, put like a no or like a, yeah, you can put like a no in the chat if you want to do more lectures. Okay. It seems like most people want more hard problems. Okay, more problem solving. Okay, so I think for next week's lecture, we will do more hard problems, and I won't be like talking as much about theorems and things. Instead, we'll look at some problems. Okay, I will keep that in mind. Also, I think at some point in time, maybe this was like a couple weeks ago, I think we sent out like feedback forms. So if you guys want to fill that out, that will help me like adjust the curriculum and stuff. Okay, actually, one thing, we will not have class next week because of fall break. I forgot to mention that. I'll send an email just in case you guys forget. We will have class the week after. So no class next week, both for this class and algebra. Okay, amazing. Cool. The feedback form should be sent to your parents' emails, I believe. Okay, awesome. Cool. I think we're doing great. All right, so let's go ahead and end for today. If you guys have questions, feel free to stick around, and I will make sure that our class next week focuses on some pretty tough and challenging problems. All right, bye everyone. Thank you so much for a great class. Have a wonderful fall break next week, and see you all the last week of September. Okay, bye everyone. Bye, Jason. Bye, Mari. Oh, hold on. I do see. Oh, Shonix asked about an algebra problem. Yeah, Shonix, send me an email and we can talk through that. Yeah, you can definitely send me an email. Okay. Yeah, bye, Sanvi. Bye, Rohan. Bye. Yeah, bye, Dharav. Thank you so much. Bye, Ditya. Bye, Rohan. Yeah. Okay, Shaunik, you sent it in an email. Yes. Okay, I will get to that and we can talk about it there. Yeah. Thank you for asking questions. I really appreciate it. Okay. Awesome sauce. Alrighty. If no one else has any other questions, I am going to go ahead and end. If something comes up, feel free to reach out via email. All right. Bye, everyone.